This is Unit 3, Moles and Stoichiometry, Lesson 6, Percent Composition. How do we calculate the percent by mass of an element in a compound? By the end of this video, you will be able to calculate the percent composition of a substance, and you will be able to calculate the percent composition of water in a hydrate. So do now. So a real-world example of percent composition are the nutrition facts on all the foods we eat. Nutritionists have taken our food and they've actually calculated each ingredient, fat, cholesterol, sodium, carbohydrates, all the things we learned about in living environment. And what they can do is they can calculate the percent composition of each of those items and then tell you about how much that is for your daily diet. So this percent composition is a really important concept for us to understand. So the percent composition is the percentage by mass of each element in a compound. We are going to use the formula located on table T on your reference tables, which says the percent composition by mass is equal to the mass of the part we're looking for, divided by the mass of the whole times 100. So calculating the percent composition, we're going to take two steps. One, you need to calculate the GFM of the entire compound. By nature, that will get us the mass of the part. So we'll do the whole as the GFM, and the part will be part of that calculation. Then we're going to plug that into our percent composition formula. So, for example, what is the percent composition of calcium in calcium chloride? So the GFM of calcium chloride, I'm going to take each element. There's one calcium and two chlorines, and I'm going to multiply by their masses. Calcium on the reference table is 40.0, and chlorine is 35.5. So 1 times 40 is 40, and 2 times 35.5 is 71. Add those together, I'm going to get 111 grams per mole is my GFM. Then to calculate the percent composition, I'm going to take the mass of my part, which I calculated right here. 40 is the mass of calcium, divided by the mass of the whole, which is going to be 111, times 100. So when I do that math, 40 divided by 111 is equal to 0.36 times 100 is going to get me 36% calcium. So here's example 2. What is the percentage by mass of carbon in CO2? So carbon, oxygen are our two elements. We have one carbon and two oxygens. Carbon is 12. You have to look on your periodic table if you don't have that memorized. Oxygen is 16. Look on your periodic table if you don't have that memorized. 1 times 12 is 12, and 16 times 2 is 32. I'm going to add those together, and that will get me 44 grams per mole. That is the GFM of carbon dioxide. So now I want to find the percent by mass of carbon. This is going to be my part. This is going to be my whole. So the part that I calculated is 12 divided by 44 times 100. That will get me the percent composition of carbon in carbon dioxide. So 12 divided by 44 is 0.27 times 100 will get me 27% carbon. Okay. 1 second. Here we go. Delete this. Here that is listed out so that you can double check your work. Example 3, what is the percent by mass of nitrogen in NH4NO3? So following our same strategy, calculate the GFM of our whole compound. We have nitrogen, hydrogen, and oxygen. There are 2 nitrogens. Make sure I count both. Look, 1, 2. There are 4 hydrogens, and there are 3 oxygens. Multiply by their masses from the periodic table. Nitrogen is 14, hydrogen is 1, and oxygen is 16. So 2 times 14 is going to get me 28. 4 times 1 is going to get me 4, and 3 times 16 is equal to 48. I'm going to add those all together, and that will get me the GFM, the gram formula mass, 80 grams per mole of ammonium nitrate. Now I want to find the percent of nitrogen. So 28 is my total mass of nitrogen in this compound. My total mass of the whole is 80 times 100. So 28 divided by 80 is equal to 0.35 times 100 is equal to 35% nitrogen in ammonium nitrate. Here is that work listed out so you can double check. Now the percent composition of hydrates is very similar. A hydrate is an ionic solid with water trapped in the crystal lattice. So it is written like this, the ionic compounds formula, and then we're going to put this dot times the number of waters in that compound. So for example, here's my ionic compound, copper sulfate. Here's that dot, and this tells me I have 5 H2Os. So the dot shows that there are 5 H2O molecules attached to the one copper sulfate molecule. And so this is an important formula for you to be able to recognize and identify the different parts. An anhydride is a crystal with no water trapped inside its lattice. So this is the opposite of a hydrate. So what gets trapped in the crystal? Well, crystal lattices have open spaces between the atoms, so water molecules can get trapped in those spaces. It's like the food between your teeth. Water molecules have charged ends, which are attracted to the charged ions in the crystal, so we'll learn lots more about water later. An everyday example of a hydrated crystal is the little white packet in your new shoebox that says silica gel do not eat. These are anhydrides, and they absorb the water from the air so your shoes do not get mildew on them. We also use these in electron packages. Also in medicines like Tylenol, they put those little cylinders. Those are anhydrides that absorb water. So to calculate the percent composition of a hydrate, you're going to first calculate the GFM of the hydrate, including the water, which is going to be our mass of the whole, and then plug into the percent composition formula on table T. If heated, the water in hydrates evaporates away. So any difference in starting and ending mass of a hydrate is the mass of the water. So what is the percentage by mass of water in sodium carbonate crystals? So first we're going to calculate the GFM of the hydrate. So we have sodium, carbon, oxygen, and water. We're going to count water as a separate unit because we want to find the percent of water. Percentage by mass of water is our part. That's our part. I have two sodium, I have 1 carbon, I have 3 oxygens, and this 10 in front tells me I have 10 waters. Times sodium, if you look on the periodic table, is 23. Carbon is 12. Oxygen is 16. And water is 18. So 2 times 23 is 46. 1 times 12 is 12. 3 times 16 is 48. And 10 times 18 is 180. Add these all together, and we will get the mass of our whole, 180 plus 48 plus 12 plus 46. I got 286. So this is the mass of the whole. Our part is going to be 180 times 100. So 180 divided by 286 is equal to 0.96. That doesn't sound right. 180 divided by 286 is equal to 0.62 times 100 is going to get me 62.9. So I'm just going to round to 63% H2O. All right, the next, plug values in a formula. All right, so I did that all on the same slide. So here you can check your work. Step 1, calculate the GFM of the hydrate. So this should match up with what I did. They didn't round in this, and that's okay. Step 2, plug into the values. Here are the values that I plugged in, 63%. Percent composition. What is the mass of water in barium chloride? So following our same steps, barium chloride and H2O. I have 1 barium, 2 chlorides, and 2 waters. Barium from your reference table is 137. Chlorine from your reference table is 35.5. And water is 18. So 1 times 137 is 137. 35.5 times 2 is 71. And 2 times 18 is 36. Add those up, and that's going to get my mass of the whole, 244. So I want to find the mass of water. That's my part. So it's going to be 36 divided by 244 times 100. So 36 divided by 244 is going to be 0.147 times 100 will get me 14.8% water, H2O. So this, check your understanding. Do these 2 questions. And now you are able to calculate the percent composition of a substance and calculate the percent composition of water in a hydrate.